What are we going to do here? Acoustic fluid properties and fluid substitution consequences. All right. Mike said a few words. He's tried to steal my thunder again there a little while ago about fluid properties. But I'm just going to tell you that we're going to talk about, earlier I said, you know, we got K-sub-Fs and Rho-sub-Fs, and they're going to vary, and there are other kinds of things. You can look them up. Well, we're going to talk about what some of those properties are that you can use when you go in the calculation part of the logic. The first thing I want to do, however, is to introduce you to some picture, some idea, some assessment of uncertainty. If you were to take those Gaussian equations, just that VP equation, and you were to write it down as, look, I want the gas velocity equation, and I want to write that less the VP of the brine saturated velocity that I entered with, and you did all the substitutions that you have to do because you solved the first equation for the beta, you'd find out that you have a scalar equation in about 11 unknowns, 10 or 11 unknowns. It's a complicated equation. You've got a lot of different parameters to enter. So the natural question is to ask yourself, well, that difference in velocity that I was showing you on that plot where you had the velocity curves changing as a function of the input velocity. That difference in velocity is a function of a lot of different variables in the 11 to 10-dimensional space or whatever it is. So what I want to do is to calculate the derivatives in each direction, and I need to do that at any point I want to do it at. I got a little program that'll do that. We're going to just look at one such point, and we're going to do an oil case, and we're going to do a gas case. Okay. Here we're looking at a water saturated velocity of 81.42 per second and a porosity of 30%, and here 25% water saturation. And these parameters are essentially for silicon dioxide, that's the grain parameter. These are for brine, sigma sub 0.2, and then here's my oil and here's my gas. They depend on the reservoir conditions. We're going to go through that in a little while. And look, I don't want a partial of velocity change, which is in feet per second, let's say, with respect to each one of these parameters which have different units. That's tough to compare. So instead what I'm going to do is I'm going to say, hey look, I'm going to change each one of these variables by 1% from what I started with. And I want to know how much the velocity difference changes. The velocity difference I calculate changes. And I can compare them all, their relative sensitivities. Okay? In other words, I know them. I know them to some precision. Which ones do I have to know to more precision to get a more accurate answer, a more precise answer for the difference in velocity? Well, here's the answer for this particular point in space, and it will vary a lot depending on where you are. But this is a typical kind of reservoir situation. Okay, so what does this mean? Here's 0. I can be either positive or negative. I might change it, but if I increase for example, the water velocity, I increase the velocity differential for the oil and for the gas case too. If I increase the porosity, I decrease. So it has a sign. I decrease the difference in velocity I'll calculate. Now, what you do here, if you have sensitivity problem, you say, well, which ones are the most important? Well, these guys are the ones to which it's most sensitive at this point in that 10-dimensional space. The water saturated velocity that you input and the water velocity you input. Anybody got any idea why that is? Same thing over here. Velocity is fairly important. The rest of these things don't count very much. The reason that is because this thing and this thing are what determine beta in the low and the high porosity, the low beta case. I should have put beta up here. I didn't do it, but I should have put it up there. These things are, remember that equation and what's in it. You have these two terms, and these two things, the V, because K depends on V squared, so it's most sensitive to the velocity of the, I'm sorry, V water, of the brine, or in this case, water, I said water. And to the water saturated velocity. We saw the water saturated velocity on those plots I showed you as we moved this way, those curves should change quite rapidly. So what we have to know is something about what affects the velocity of water, and we're going to have to get good estimates of the water saturated velocity, velocity-porosity pairs. Otherwise, we're not going to be able to make very precise estimates of our calculated reflectivities. That's what that's all about.
Well, if you go back there for a bit too, I mean, this is also quite instructive, because you can see that, for instance, in terms of these sensitivities, and what you need to know and don't know, that right here, notice sigma sub m is probably one of the smallest things sensitivity-wise, okay? And remember, we were just saying that in order to know the amount of the Gaussian substitution, you can just put in a rough idea of this because the sensitivity is so low. Okay, another thing though, you know, especially...
Here's another one, that's W, where we have that flat curve from the suspension formula. So it's practically insensitive at 20%, 25% water saturation. It's flat, doesn't care. But if you move over to, 85% or 95%, it'll be much higher.
Right, and then also something else that's called up. I mean, this one in terms of the water saturated velocity, I mean, that's the one we measure and we think about a lot, right? But there's another thing though, that in terms of low beta rocks, watch out for this, okay? And that we tend to get lazy sometimes when we sort of say, what's the in situ brine, okay? And in very low...
Don't steal my thunder, it's the next slide.
Okay. Okay, and so, but you're pointing out that you do have large sensitivity to what's really sort of effectively the salinity. And we'll get to that, but it's in for the lowest beta rocks that you have the problems with sensitivity.
Of course. Okay, so here we are. This is, might want something that you could easily interpolate. And so we use Gulf of Mexico kinds of numbers, if you like, for temperature gradient. As we go down in the earth, what happens? The temperature increases, the pressure increases, and depending upon what you have here, in this case we have brine, oil, gas. So use different colors for the different fluids, so you get some idea of that. And in the case of brine, we have fresh water all the way up to saturation of chloride, sodium chloride. So this is chloride. So what do you see here? First of all, as you increase the pressure, we're looking at density. As you increase the depth, which increases both the temperature and decreases the this is actually, it's for, this one is for, there are going to be two sets of slides. One is for shallow water, Z water equals 0. The other is going to be for deep water, 6,000 feet water depth. And everything will be as a function of depth sub sea bottom, if you like. Okay? That's what this is. We assume normal pressures, not over pressures. Okay, so what happens? You increase, as you go down this way, you increase the temperature. Gulf Coast temperature gradient is like 1.2 degrees F per 100 feet. We convert that into C, what degrees C per meter or something, but you can do arithmetic as well as I can. The pressure is increasing, normal pressures, I told you about that before. Brines are like 1.05, so it's about 0.46 or 0.47 psi per foot. And you can see that the density is a 10% effect from salinity for the whole range of salinity and the density. Not too bad. What's happening here? Why are these curves diverging? By the way, this is based on some empirical work and is not something you can calculate from first principle. It's more an empirical correlation of data based on physical ideas. Well, what's happening is as you go deeper, you get higher pressure. The higher the pressure, the greater amount of gas you can dissolve into oil. And therefore, the oil gets more compressible even though it's dissolved. That gas is a lighter hydrocarbon and it's a lot easier to compress even though it's dissolved than is the oil, the longer hydrocarbon chains and more complex molecules that are around them. So or what happens is these things diverge as you go to higher pressures. I put a number of gases on here. It's important to remember that most natural gas is largely methane. I'd say quite commonly methane constitutes more than 90% of the natural gas you will find, but certainly more than 80%. Other common components are nitrogen and sometimes some H2S, as you well know, not usually very much. Sometimes CO2's in there, whatever, but mostly it's methane. And for most everything else, I'm going to use methane. These are empirical equations of state. That's where these numbers come from, and I just put ethane in here because it's the next highest compound, next highest paraffin compound, and it's the equations of state was available. Notice that what's happening is that the density goes roughly like the specific gravity of the gas. So nitrogen is what, atomic number 28, and methane is CH4, what's that, 16. So it should be 2 to 1 roughly, and it is. And that's typical. Oh!
So why does it density press the
Why is what?
that's density for you guys?
We're gonna go to velocity now. Well, maybe I'm gonna go to 6,000 feet of water first. That's it. And hey, it still works. 0.2, 0.4, something like that.
So depth on the bottom of it.
Yeah. Depth below the mud line. Depth, sediment depth, that's what I should call it. I should have called it sediment depth. These have diverged more. Why? Because I've got higher fluid pressures. I've got that 6,000 foot water column.
Why was the drainage down? I must have missed something for the, say, for the brine.
Speak up.
Say for the brine case, why is it becoming less dense?
Less dense?
Increasing depth?
The dominant effect is got to be therefore temperature. That's interesting. Picture of it. I'll show you something like that. Velocity at constant pressure, the brine, as a function of temperature, looks something like this. Not the velocity. The density. I got to be careful. I want density. I better not. Well, this is what's velocity. I don't know. It's got to be temperature though, because I know that that at higher pressure, of course, it's going to get more dense, and so the pressure's increasing, and the salinities are constant here, so it's a temperature effect. But it's a very minute effect. I mean, look, we're looking at, this is a non-suppressed scale. We're looking at, 2 or 3% of that whole.
Is that the same for gas saturators as well? The green gases?
This is dropping, both of these drop, yes, because of temperature primarily, but this one more so because of the greater amount of gas you're putting in as you get to higher pressures. That's what's happening.
I want the CO2 to go first.
CO2,
Perfect.
I already told you, but I slipped it in between the lines, Mark. CO2 is 2 oxygens, that's 16 double, that's 32, and a 12 carbon, that's 44. So 44 relative to 16 is going to be about 2.5 or 3 times whatever methane is density. That's where it's going to be.
That's what it looks like.
Yeah, it's going to look like, what is this, what is this, about 0.23, so it's going to be, what did I just get done saying, 2.5 times 0.23, that's about 0.6.
Yes, that looks like a gas
It's
saturated.
going to look like a gas saturated oil. Density, in density. Let's look at velocity. Okay, we're back to no water color, shallow water. Remember all these pictures, which may not be so clear, I don't know which ones are clear or not clear, but there's a lot of them that aren't terribly clear in your book, but they're on the website. So, here's the fluid velocities. Salinity makes a difference now. I didn't label these the salinities. This is obviously the hot 200 grams per liter. This is 0 grams per liter. It's a significant effect. So you need to know the salinity This is a 10% difference. And as Mike pointed out, and I pointed out, that V water is a very important parameter. The velocity difference is very sensitive, that you will calculate is very sensitive to V water. So what's that telling you? It's telling you that you're going to have to know pressure and temperature when you do that, and salinity for brine to make a good estimate. And you can interpolate between us pretty good. Here's the oil. Here's the gases. And what I'd have you notice about the gases is it really doesn't care that much what the density of the gas is, what the velocity is. The velocities are quite similar. I mean, not perfectly the same. And as you get to higher pressures and temperatures, this is pretty close to the same thing. Not suppressed scale on purpose. So a rough rule of thumb is for gas, hey, use the numbers for methane. If you have a different gas, if you know its density or its specific gravity, then you can calculate that even from its atomic number. Scale a density by the atomic number and use the same velocity as you have for methane, and you'll be fairly close. And you don't need to know the gas properties so tightly percentage-wise, because that term, that second term in the Gaussian equation, is going to decrease a great deal, because it's the contrast between the bulk modulus of the gas and the bulk modulus of the brine that makes the big difference in that term. And if you change this by 10%, you didn't change the contrast much at all. You change a small number by 10% relative to a big number, you haven't changed the contrast much at all. Okay, the deeper water case, you've increased the actual values, but the difference in salinity is still there. And same story holds true. It's not quite as good for the people that are with the high pressures, you know, a little bit of variation. But CO2 is going to be still up for, like you said. Why is this thing truncated? Because I didn't have the data in the empirical correlations at full saturation for this kind of pressure reservoirs. So I sort of chopped that off. Okay, now we're talking about the bulk modulus. That's the one we really want. We want the density in the bulk modulus. But look, the big news here is there's a difference. You need to know the salinity, and that gas is different from oil, is different from brine for the most part, unless you get to very great water column depths, high pressures, high fluid pressures, where gas can begin to look like oil, saturated oil, if you have saturated oil, and that's the real takeaway. Same thing holds true for the deeper water. This is a picture Mike asked me to put in there. This is for your benefit. We'll talk a little bit about reservoir. This is what gas to oil ratios look like for a mid-range gravity oil, 30-degree gravity oil, as a function of depth, again, with those same Gulf of Mexico kind of parameters for the temperature gradient and normal pressures, with the shallow water case and the deep water case. This is saturation. Okay, this is the amount of gas this oil can hold at saturation for those various depths, normal pressures. Okay, now this is something like gas. I'm going to take a brine that's in the mid-range of salinities. And Mike, well, why don't you give me some sensitivity for these parameters? Okay, here's density. This was the initial condition, right? We're going to do the same thing we did in that first slide. Only instead of looking at the velocity difference of a porous rock now, we're simply looking at the difference in the properties of the fluid, okay, as a function of the variables that go into control it. So this is again the percent change due to a 1% change in the property. And what do you see here? Well, you see, let's look at this one. It's the one that counts. It's the big one that counts. And what it says is, hey, you got to know salinity and pressure and temperature. You don't have something that's close and something that's far away. You got three that all have an effect, similar type of effect. You got to know them all. The oil property sensitivities, instead of 30 gravity oil, I used dead oil. That's what they call it. Oil that doesn't have any dissolved gas in it. 22.5 gravity, had to do with a particular field, what it was, at Mike Atlantis or something. Anyhow, here's the picture, and the long and the short of it is, you have to know. Well, it's not surprising, you gotta know what the API gravity is. That is the density. It's just a different way of saying it, the density of the dead oil, of the tank oil, stock tank oil. And you gotta know the pressure, and you gotta know the temperature, and just a little of gas oil ratio too. I could have put in here average gas specific gravity of the dissolved gas. It doesn't really make much of a difference. That's something that hangs around zero.
But that gas oil ratio is 0. That is one.
Yeah, right, and that says that, well, I'm sorry, percent change, so this is the percent change, and I don't know what I did here, I don't know how much I changed it, it's a good question, I'll have to go look. It's obviously not 1%. That's a good question, I don't know what that, mark that down when you feel, what slide that was, 17, please. Okay, this is the gas saturated case, and gas oil ratio is not terribly important really compared to the other ones. It's the least important. Here's our gas, same kind of thing. Our gas. You gotta know pressure and temperature. What else to? Pressure is more important than temperature for the bulk modulus and for the density. I told you that before. Now, I wanted to talk a little bit about, I got two view graphs here, about reservoir conditions. You know, when we produce a reservoir, we get, if it's a gas type reservoir, you get some gas typically, and you get some condensate, what they call condensate liquid. And if it's an oil, typically you also have to have a separator to produce both what's called stock tank oil and then some gas, dissolved gas typically is what it's supposed to be. In the ground, well, let's not talk about it in the ground. Let's just talk about a single fluid, let's say a single compound like water. I can have a pressure temperature diagram, a phase diagram, this is called commonly, and at low pressures and low temperatures, I have a liquid phase, and at higher temperatures and the same pressures, I will have a vapor phase. So if I'm dealing with water, for example, and this were for water, down here I have some high pressure and some not very high temperature. I have a liquid, and as I raise the temperature, I get over to here. Along this curve, both phases can coexist. The gas phase and the liquid phase coexist. They're in equilibrium. As I raise the temperature some more, hey, that water boils, everything goes to steam. If I leave it on the stove too long, I've done that, fall asleep, boiling coffee water, wind up with a dry pot. Okay. This is called the critical point, and it's often thought of as, well, I'll just say it the way you should think of it. The critical point is that point at which all the intensive properties of the physical properties, all the intensive physical properties of the compound are the same, whether in the gas phase or the liquid phase. That single point on the equilibrium curve, on the two-phase curve, where the intensive properties are all the same. So what do we have? Up here, we have a single-phase fluid, and here we have a single-phase fluid, and down here we have a single-phase fluid, and down here we have a single-phase fluid, and it's quite common to think of this as a liquid-like single phase, of this like a gas-like phase, in the following sense, that, if I go the other way, by the way, over here, this is, your cool fall morning in a humid area. You drop the temperature at constant pressure, and you get dew out of the air on the grass, right? That's what happens if you go this way. But you could do the same thing over here. You could drop in a different way. You could keep things at a constant temperature and drop the pressure. And what would happen if you have a liquid reservoir? What would happen is you would get gas to bubble out of it. It was a single compound. So you would lower the pressure, like when you take the top off a can of beer, bottle of beer, so you can see it. And up come those little bubbles, right? That's what's going on here. You're keeping the pressure, the temperature the same, but you're lowering the pressure. And out come those dissolved gas bubbles. That's like what you do in a reservoir. Okay? Now, oil isn't a single compound. Oil is a complex compound. Each oil has different bunch of mixtures of compounds in it. So let's go to the next level of complexity. And that single phase equilibrium curve becomes a region in which the two phases can coexist. The whole region. And the critical point where the intensive properties, this is a particular, what is it, ethane and N-heptane combination. These pictures are both taken from a work by Stanley, 1951, Miles Stanley, worked for Chevron, very nice monograph. If you are interested in getting briefly and quickly informed a little bit about the fundamentals of reservoir engineering, it's a very nice little monograph to look at. So now we have a single phase region over here, and a single phase region over here, and everything, of course, above that line is a single phase region as well. And this region from here down to here is commonly called the bubble point locus, and this the dew point locus. Well, why is that? Because if I had a reservoir and I was up here, let's say I had a reservoir at this temperature, was that 150 degrees or something, F, and I drop the pressure, which is what you do when you drill a hole in it. It's at a constant temperature. It's going to stay as a constant temperature because it's got a big temperature bath down at the bottom. You do this, what happens? Gas comes out of solution. Sorry, when I said, yeah, no, this is above the critical temperature. This is a dew point. So what I have is little liquid drops show up, my condensate out of my gas. And in fact, if you looked at the contours internally in here, if you go far enough down here, you get more and more condensate as you lower the pressure. You lower enough, you start getting less and less condensate again until you get down here, in which case you don't have any condensate anymore. You got a dry gas again if you lower the pressure enough. And if you were on this side and you do the same thing, then it's a liquid-like. This is a liquid. This is liquid-like single phase. And if you lower the pressure, you get what's called a gas, solution gas coming out that you have to separate up at the surface at low pressure. And this is bubbling up like the bubbles in beer. This thing is called the tricondentherm, of all things. And what Standing points out and what I'll show you on the next slide is very nice. Let's just talk about this thing first. Gaussian equation, we talked about sensitivity as a function of many variables, but it's especially sensitive to VW and VW sub F. The bulk modulus of brine depends on pressure, temperature, and salinity. You really need all three to estimate the change in velocity. I shouldn't say accurately to get an accurate number, but well, you need it accurately. You need it accurately. For this, you need accurately. You need all three to do it accurately. That's correct. Most natural gas is composed primarily of methane. That's useful because that's the properties you should concentrate on in your book. The density of methane at high reservoir pressures is substantial. Could be up to half that of oil. The velocities of gases depend chiefly on the pressure and temperature, and not that much on composition, while the densities roughly scale the gas percentage of gravity. That's the rule of thumb. And roughly, that's crude, but it's good enough for the calculations we do for gas. Oil property is trying to separate gas effects from oil or brine effects. Oil properties are complex, but can be roughly predicted from API gravity, GOR, pressure, and temperature. That's enough information to do it. These are the kinds of things you might have available to you from previous fields in a basin. That's why I characterize them this way. And in almost all conditions, the bulk nodules of brine is greater than that of oil, which is greater than that of gas. I talked about that earlier this morning.
And also, I mean, let me just make one, if you go back on the previous one, I just want to make one point. Is that when it comes to oil properties, and that we did establish here that they both are functions of the gas-oil ratio, the API, the pressure and the temperature. They're fairly complex relationships between those. As Dave said, they're primarily empirically based on top of some particular sort of fitting functional forms that make some sense from a physics basis. We do subscribe purposely to the University of Houston and the Colorado School of Mines Fluids Consortia. And a major reason for this is to get access to their fluid spreadsheet. And what happens is you enter these four numbers and they'll tell you what the VP and the density is of that oil, so that we can have that for our other sort of follow-on amplitude predictions. So I just wanted to go and say that's practically what happens. The stuff for a gas, to a large extent, is fairly close to a standard sort of gas law. There's nothing really dramatic about that. The salinity is, and the brine properties are also fairly straightforward relationships, but oil is complicated, but there is a particular sort of program.
That's a good resource too. I do endorse that. The guys that ran that, Mike Batzel and Dave Wahan, they did a good job. It's not fly by night. It's science. It's good stuff. Good measurements, good results, and that's important. It's a very important point Mike just made, because oil is an important one, because oil is close to brine in its properties, much closer than the gas. And so if you suspect that you have an oil reservoir, you have this slightly more intense amplitude that seems to fit structure, do other things, and you say, that could be an oil reservoir. You really want to calculate that as well as you possibly can. So it's very important to look up the numbers and try to get the numbers that are characteristic.
And also, I mean, we've, I think that here you've experienced a lot of, you might call them false positives, or at certain times predictions that were a bit surprising, that came from oils that were bouncier, or had I mean by bouncy, had a lower bulk modulus than you'd expect, or vice versa. And so paying attention to where you are in that phase diagram and what the potential oil properties or condensate properties are is something to pay attention to, especially in this area of the world.
So let me do the last two on this thing. And this is long-winded stuff. In reservoirs which produce both liquids and gases, the wellhead, the fluids in that reservoir, there's an A here that's silent. Invisible too. The fluids in that reservoir may exist in two separate phases, or they can exist in a single phase, depending on the composition of the hydrocarbon fluids and the pressure and temperature of the reservoir. We just did that. When we did that N-heptane, ethane combination, showed you that there's a region in there where you could have two phases, higher reservoir temperature, or liquid with dissolved gas, lower reservoir temperature. And you haven't got control over that, but you do have control. Some producers do fool around with their pressures at the wellhead in order to change their condensated gas if they have wet gas, because as prices change for the liquids relative to the gas, they may wish to get more liquids out or less, and so they'll change their pressures accordingly. Okay, enough said. I think it's good time to take a little break, don't you?
Yeah, that's good.
That is, that derivation, he's not giving us the derivation, he told us some restrictions, and he's telling us what the equations predict. But it's reasonable us to ask is, well, great, that's what they predict. Do we have any evidence that that's what happens? Being an experimentalist, I think experiment is always the where you have to go. Galileo taught us that, and you got to pay attention to observation. So let's look at some observations and compare them with the predictions. This is that same picture, but now redone, that I showed you before from Wiley, Gregory, and Gardner. Sandstone cores, linear in transit time, increasing, decreasing velocity, nonlinear. And I don't want you to focus on this time average stuff, that's not important. The important part is that this time, I said, well, let's just do something simple. It's not the hardest thing you could do, it's the easiest thing you could do. Let's take all these water-saturated velocity measurements and just fit least squares quadratic curve to that. Then we have, at each point on this curve, we have the porosity and we have the velocity of the brine saturated, or water, in this case, water saturated core. What do we need to enter the Gaussian? We need the velocity, the VP, and a porosity pair, right, with a known fluid. So, great. We can transform this curve point by point using our fluid substitution logic. And I don't know what I used here for sigma cement, but I guarantee you I used something close between 0.15 and 0.2. And here's the result. And these are those drive points that he measured. Not a bad fit, huh? That's, I mean, you know, it's a little on the high side of these data, perhaps. I mean, if you drew a curve to fit these, you wouldn't draw it, well, you might draw it something like that. It'd be a little lower up here, I think, but it's pretty close. So it tells you that Gaussian, in a crude sense, is giving you reasonable answers for predicting the drive velocities from the water-saturated velocities. That's what it's telling you for sandstone cores. That's the first thing you consider. Okay, let's look at some specific cores. These are some measurements that we did in the laboratory at Shell many years ago in the 70s. In this case, a brine-saturated sandstone, 23% porosity, fairly consolidated rock. And, you know, this is in the days when you had draftsmen drawing graphs. So it's been copied a few times, so I'm going to have to read it at you. This is V sub S, feet per second. And what's happened here is we've taken the core and measured it at different saturations. How do we know what the saturation is? Well, we know how much we dry the core out, we measure it dry, then we can imbibe fluid, right? And we know how much liquid we let into the core. So we assume a uniform distribution, which may not always be true, but that's how we get the number of the saturation where it plotted. Then we go to the other end, take that core, demount it, saturate it under pressure, and we have the water saturated value. And we can drain it, so we can get some non-imbibition but drainage numbers that are closer to 100% saturation. So that's how we got some of these numbers. And each case, at each saturation value, you could measure the velocities at different differential pressures, but always with some significant pressure on the pore fluid, except in a dry case, so that you would not have gas when you think you have. That is a significant pressure with the unsaturated case. Well, at very low pressures, we couldn't get any signal through water saturated. This is water saturated. This is SW at the bottom. Okay. What do we say about Gaussian? We said that the velocity, as we put in the lighter fluid, like hydrocarbon, the lighter and more compressible fluid for the more dense water, we ought to increase the velocity of the shear. So let's look at the upper one where we have higher pressures and differential pressures. This, by the way, is differential pressure of 10,000 psi, which is too much, really. But it's a consolidated core, so I've seen that before. These dots are 6,000 psi. This is 2,000 psi differential pressure. So here we are here, and this is a curve that is the square root of the density, the inverse square root of the density curve that comes out of Gossman. That best fits all these data. In other words, it doesn't start really at the water saturated curve, but it goes through that. And this is the uncertainty of measurement based on the transit time, the uncertainty of how well we can pick the waveform and do the length of the core at these pressures. So what do you see? You see, hey, pretty good fit. It certainly rises in every case. The data do fit this curve, this kind of curve reasonably closely. It's just one standard deviation error bars, so they're really a little larger than that in 2 standard deviations. The long and short of it is, that works reasonably well. What about the VPs? One other thing I should say, and it's important to say. Somebody asked, what happens if you change the, who was it, David? Is that you? If you do the shear velocities? Yeah, that's what I thought. Do they change with differential pressure too? Well, now, do they? This one isn't here, but it would be here, it'd be close here somewhere, if we had gotten signal through at full water saturation. So surely they do. This velocity is 5,600 feet per second. This one is at 63 or something. This one is at 65 or 66 or something like that. So they increase the differential pressure just like the P velocities. And next, let's look at the P velocities. Same core, VP versus saturation. In the case of the compressional wave, it's easier for us to get signals through, so we could get signals all the way down to 500 psi. In this case, differential pressure. Now, we have air at what is essentially atmospheric pressure, or in some cases up to 100 psi in the pore fluid system. Still, 100 psi is nothing. Okay, it's the air at 100 psi is very light and very, very compressible. So if you do the calculation, this curve comes down right away. The curve due to the suspension formula, the resultant K due to the suspension formula comes down right away. And this is all just a loading of the density factor over here, so it rises. That's why these things all come down so sharply. This is a 23% porosity rock, and so this is this shape of this thing is a confirmation, or lack thereof, of the applicability of the suspension formula, okay, for the composite fluid. What's a test of Gossman? What's a test of Gossman is, how far did this velocity drop relative to the prediction over here, let's say, or at any point down here. What's changing here? Why is this difference? Why is this difference? Why is this difference so much bigger than that difference? VP is 11.8 or 11.6 or whatever that is here. And porosity is, well, maybe it's a little less than 23% of that differential pressure, but not much. That's your velocity-porosity pair. That's going to be a high beta rock. Remember our beta picture? It was as a function of water-saturated velocity. The water-saturated velocity here is higher at similar porosity than down here at 500 psi, where it's only 93 or 9400 feet per second. So the beta here is bigger for this rock at high differential pressure, water-saturated, than it is for this rock. This difference, this calculated difference, the magnitude of this curve based on this point and its relationship to these data points is a test of Gossman. And look how good that fit is. In other words, if I take this point, I could have predicted with Gossman that that curve could come down like this and the data would be all up here. Not so. It's not what happened. Well, it's an extraordinary fit to the data. And that's what the confirmation is. The P velocity drops like it's supposed to drop. Right? This point is higher than that point. This point is higher than that point. This point is higher than that point. That's what it's supposed to do.
I'm a bit surprised. Why it looks like somewhat unstable, like as the saturation goes to 1, just very tiny change in the saturation will cause a big change in the velocity.
Yes, and that's what I said.
Yeah, why is that physical?
Because-
I got really confused.
Because the gas is so compressible that as soon as you put that little bit, it's your beer bubbles, the gas is so compressible. This air we're breathing has a density of 0.00125 grams per cubic centimeter and a velocity of 1,100 feet per second, dry air, atmospheric pressure. Remember what we were looking at before? You 1.1 squared, right, times that density is a K that is so low relative to the K of water, the bulk modulus of water. It's more than 100 times difference, 1,000 times. You don't have to calculate what it is, but it's hugely different. So it makes that second term of the Gaussian equation through the suspension formula just go away. As soon as you put a tiny amount of gas in that air, the bulk modulus of the composite system from that Royce formula goes to something very close to the gas modulus. That's why. You've got a stiff spring in series with a very, 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 very weak spring, a watch spring. Car spring in series with a watch spring. Squeezing, which one go? What's the spring constant of the composite system? It's the watch spring. That one compresses all. That's what's happening.
Just wondering, David, those values there for a 0.9, there does seem to be a system out of
The curves.
yeah.
Yeah. Good point, Guy. And the answer is, well, we don't show typical data, right? We show good data. This is a good one. We think that has to do with and some are much worse. The saturation agreement isn't always as good. We think that has to do with distribution of the fluid in the pores. You're using so-called ultrasonic frequencies, the wavelengths of which are necessarily not too long relative to the core length, which is only an inch, and yet long enough to be much larger than pore size. So you have to be, you're in a delicate balance. And so if you have not quite homogeneous rock, you could have regions of the core which have higher saturation than others and paths through the core which the wave sees that are quite the calculated average saturation. So that's basically the reason we think that some of these data points don't follow that curve precisely.
Yeah, but again, I'm just going to sort of jump in and try to highlight again. I think, again, sort of the remarkable part of it is that once you have this point, okay, the rest of this, there's not another free parameter in here that's being fit once you end up determining what this initial point is. And Greenman, you actually are pointing out the reason why CSEM is so valuable, okay? Because this is at atmospheric, and at depth it ends up being not quite this dramatic. But very small changes and just putting a few bubbles into this, okay, causes almost the whole effect in terms of a change in reflection coefficient. A few bubbles of gas obviously is not economic. You want to be over in this area. But the way to go and discriminate against this is obviously conductive. It's not going to be resistive. It's not going to get resistive until you get over into this area. And so this is really the most sort of the end member case of how extreme fizz gas can be, okay? When you go up to, let's say, 7,000 PSI, this ends up being,
You'll see that later.
You'll see this later, that this ends up getting rounded off, okay?
Okay, question. Is Gaussian going to work for carbonate? Gaussian fluid substitution, is that going to work for carbonate? Come on now, we got some brave soul here. We got a no over here? You don't know. Well, that's what we got, an I don't know. We got a politician over here.
What's the question?
Is Gossman fluid substitution, which what we're comparing here, is it going to predict, well, like this one does for a sandstone, for a carbonate rock? It's going to predict velocity, fluid substitution velocity for a carbonate rock? What? Porous carbonate rock, yes, porous. Has to satisfy the, you know, I'm talking about a rock that satisfies the Gossman conditions as best we can with sedimentary rocks. That is, single pore fluid pressure, microscopically isotropic homogeneous, you know, all that stuff. You're getting close. Come
Well,
on.
you think it probably would?
Have I got a yes? Yes. Have I got a yes here?
Yes.
I got a yes here. Any no's? A lot of uncommitteds. Yes.
Yes.
Yeah. All right, I got a lot of smart people in this class. You're right. Yes is correct. Of course it's going to work. If it satisfies the conditions under which the equations were derived, then it's going to work. Right? It's that simple. That's what physics is all about, damn it. Okay, here's our, now I'm showing you in reverse order. Here's VP. Okay, a different order. But same story. 10,000 PSI. Bigger effect here than there. Well, I want you to notice something. There's some errors on this slide I'll have to point out. Draftsman errors. You know, this is right. Nice solid dot. This one should be solid just like these. So this guy goes with this. I guess Draftsman's trying to hide the problem here or something. This should be solid and goes with these. This is the one that's open and goes with these. Okay, that's correct. So, but the reason I want you to notice that is that notice that this is way the heck off where it ought to be. So is this. Should be down here somewhere. And this one's a little higher too. This one didn't do that. I didn't put the uncertainties on this graph. We didn't put the uncertainties on this graph. This turns out not to be an unusual phenomenon. That the dry rock measurement doesn't seem to agree as well with the Gossman substitution calculation as other partially saturated measurements. Not only did we observe this on many rocks back in the 70s, Gardner and Gardner at the University of Texas published a paper later in which they too drew attention to this fact for ultrasonics in their measurements. So it was independently observed by somebody else on cores. Now, one of the things you should take away from this is, and it's important to understand about this, nevertheless, the calculation is very good, starting from this point and calculating this curve for comparison with all these points. The first thing you should think of is, look, in the ground, I don't have any points where I have no water. I don't have any dry rocks. But you will see in papers, people have drawn empirical correlations from dry rock measurements of what K sub m or beta is like as a function of porosity or those kinds of things. Be careful about using those relations because if they were derived from dry rock data, because they will not. If you start here and predict this curve, you're going to get something that does this. And it's not going to give you correct answers for partially saturated or water saturated rocks. Okay? So be careful when you do that. It's most commonly done that way in academics because it takes a much less sophisticated apparatus to do it, and it's a hell of a lot easier to do, to measure a dry rock. Okay? So, and besides, what is sigma sub m, K sub m? They're evacuated matrix moduli, are they not? So they think, well, that's what they're supposed to be. Let's measure them that way. We do not know why this happens. But there are clues, and I'm not going to go into them here. In the interest of time, see if you're really interested, talk to me in a break or something, we'll talk about it. Let's look at the shear velocities. Shear velocity should rise. It rises. This is the calculated, this is the observed, this point goes with these. This point should be black and goes with these. Terrible. The agreement on that last point is terrible, but these points follow these calculated curves for the shear velocity, which are nothing more than a density. So long and short of it is, laboratory data, ours and others. Domenico did some very nice work, published first on this issue in the early 70s, and lots of people have confirmed this in laboratory data. I'm going to go to a field seismic example. This is what you see. Here's an amplitude anomaly that fits structure. Now, this is a profile in one direction, and there are two lines shown here and here that are perpendicular to it. Okay? And what you have, I like this one. This is the one I like to focus on because it's easiest to understand during a simple cartoon. What do you see here? Well, let's see. You see a reflector here on the top of what may be a reservoir, on top of a structure, which may be a reservoir. And you see a much brighter amplitude, red and blue, than you see lateral to it down dip. This intensity less that intensity should be equal and opposite the fluid interface intensity, which is what? It's this thing. And this thing isn't quite flat in time because the reservoir is thick enough that it sags a little. See what I'm saying? In time, when you get thick. And this is blue first red, that's red first blue. It's equal and opposite polarity. That's what we said before, right? That's what we should see. So that's a really nice thing. You have the structural conformance. Of course, in 3D, you could map it out in 3D.
In the next slide.
We'll see that next. But down here, this is that fluid contact, I think. And, well, you see the same things. You see the top of the reservoir and the bottom of the reservoir where it's up dip, where it's fully charged. They're opposite polarity. Okay? Same thing over here. So you have an anomaly, an amplitude anomaly that fits structure. And this is a picture of how it fits structure in 3D. This is, I mean, hopefully I ought to talk about this, but I'm going to say it. These are contours in, I presume, in depth. And this is the amplitude. And just notice, this is down dip on here.
No, that's not. That's
Oh, this is up dip, I'm sorry.
Yeah, it's stratigraphic.
That's right, I'm sorry, that's correct.
You have to take a look. I mean, this is a saddle right here. This is down dip. This is the crest.
Right, that's right.
It's going up with the stratigraphic boundary
That's it.
here. And so that the particular fit to structure is down along this contour, and this is the same 3800 contour coming back around the other side.
This thing is a plot of amplitudes in some transect like
Yeah.
This over here, notice it has high amplitudes, something like this, but it is a stratigraphic variation in the rock character, perhaps. I don't think it's, I think you don't think that's right. It has no structural component. And this over here is just his plot of the mean amplitudes over here.
So it's a mean amplitude ratio of this particular area, this divided by that. But in other words, you sort of see this is showing what the amplitudes are on average up through here versus the amplitudes here, which have been set, and we've gone and normalized things so that this is the background amplitude. And this is what, you know, the amplitude prediction was, by the way. It was about 2.5 to 1 is what is expected for an oil sand in this area.
All right, I want you to think of these last two slides, and then we're going back to that cartoon. Don't look anything like that cartoon. Okay. We didn't see this. We didn't see this here. It's hard to see it. If you go back to the first one, I'll go back there. You can imagine it, but it's hard to, you know, in this picture you can imagine. It's hard to tell the real intensity over here. We'll get to that tomorrow. We'll talk about why you might expect that bump. But we're not going to talk about it today. Okay. I'm going to say one more thing
Well, actually, you do see, if you go back here, you do see some of that effect, I think. We could go to the next one, no, yeah. Yeah, but if you go to the next
Oh,
one.
you want this one?
Yeah, that, especially right into this
No, but
area, I
that's-
think.
But that's the thicker part.
And that's where it stratigraphically pitches out.
Up dip, oh, it's thin.
It's the up dip.
They couldn't
and-
be tuned.
Yeah, we think it's tuned.
We think it's tuned.
I think the right in this area was tuning. And also, if you look a little bit closer.
Well, this definitely is thin, but that's down dip.
Yeah.
So she should be like
Yeah,
that.
so we were thinking that was probably tuned.
Okay, in any event, if you have this kind of response where you see high amplitude that fits structure, and you see a lower amplitude that is still above your background down dip, and this guy is also structurally conformable. You know, you see him around in a rim. That's probably about the best kind of evidence, if the numbers fit. That's about the best kind of evidence you could get, in my opinion, that you have oil, an oil reservoir. It's very difficult, as you will see in hub plots, in your own exercises, and in what Mike shows you subsequent to today. It's very difficult to get that oil prediction will sit between the gas and the water, and the deeper you go, the higher beta you go, the more squeezed it gets, and it's harder to convince yourself on the amplitude evidence alone that you have oil. But you may be able to do it. In this case, you're in that range. But if you get this, that's a really strong indication. Okay, so what are we going to say? What to look for? Boy, if you're going to, you got all these summary slides. As explorationists, I really urge you to pay attention to this one. What to look for? Polarity. The reflections from the top and the bottom of the reservoir unit should have opposite polarity, and they should have the correct polarity. What do I mean by the correct polarity? Let's go back to this picture real quick. See that? You got to have a softer rock. You can run some. You have to have a softer rock. At the top of that reservoir, you should be going into a softer rock. If you have deconvolved your seismic properly, and we're going to talk about that, and done your processing correctly, you should know the polarity of your data. And therefore, if you're going from a softer rock to a harder rock and it's bright, that ain't hydrocarbons. Or you've screwed up the polarity of your data, the deconvolution of it. So you should have the right polarity. Is there a flat spot? Gee, that's a big one. If you've got a flat spot, the flat spot's reflection should have the opposite polarity of the reflection from the top of the reservoir. We saw that in this profile over here, right on this last case. The geometric correspondence of amplitudes with structure down dip is very important. Gravity requires a common fluid level. It's a very important clue. That's what people look for all the time. When you're stratigraphic, you got stratigraphic variation, and often you do stratigraphic component to your trap. Sometimes this is difficult to observe. It will reduce your confidence if you don't see structural conformance, I can promise you that. For thick reservoirs, and only for thick hydrocarbon columns, I should say, the time sag on the reflectors below the reservoir indicates pay thickness. Look for structural conformance of the anomalies on isochron maps. All I'm saying is look for time sags. A two-step amplitude response, or halo, indicates the presence of an oil rim. This is perhaps the most reliable indicator. You have to have geometric, conformance with structure. That's important. And here's the kicker. It's in bold. I know it's low. Pay attention. Dollar value of a prospect is not linear with amplitude. Oil is almost everywhere more valuable than gas, particularly internationally, and anywhere else too. In the United States, it's more valuable on a volume basis. And oil has intermediate amplitudes. So instead of simply looking for the brightest amplitudes on your section, you should be looking, when you see bright amplitudes, you should be looking for structural conformance of intermediate amplitudes first. Do I have anything that I can be thinking could be an oil reservoir? That's what you want to be looking for. Okay, I think that's it. No?
Yeah.
What's important, this is experimental evidence. The Gossman and the Royce formula are in good agreement with both professional surety and loss of
Before you go to that, just wanted to go and have Pete sort of refer people quickly to this sort of the cover picture here. That, I mean, this is scaffold, it's not too far from here. And the one thing that you do notice here is that, and this is up dip and that's down dip, is amplitude A, amplitude B, and amplitude C, okay? And we'll go and take a look at, a little bit later at another, sort of look at this. But, this, and I think that in the Pyrenees area is another place which you ended up seeing sort of double flats with right amplitude ratios. That really is, a really, good indication. Another thing to also note that was, I think, some of the particular, early exploration in this area was to a large extent focused on bright amplitudes and drilling the bright amplitudes. And I think that, as we, have realized that the real prize were in two of the dimmer amplitudes, which were Enfield and Stuybarrow, okay? And by the way, the amplitudes of Enfield and Stuybarrow, it's fairly close to where this amplitude is, by the way. Ends up being about the size of that intermediate amplitude that you see here, okay? And obviously in this area, oil is worth a lot more than gas. Even though gas, if it's, the big gas here obviously is worth a reasonable amount. But anyways, it's sort of one thing to go and keep in mind as you go forward. This is probably one of the best examples.
That's a very nice example. Okay, I didn't show this here, but often you will see our logs. I will show you one of the next lectures where there is a clear case in the log, and you'll see the old log too. The Royce formula for composite fluid properties makes the amplitude response for low saturation gas reservoir quite comparable to that for first reservoir, so long as the velocity dominates the density deflection coefficient. Talked about that earlier, right after lunch, when we talked about the suspension formula and the effect on the bulk modulus and how that was going to cause, in the Gossman fluid substitution calculation, low saturation gas to look like a commercial reservoir. We're going to see it again in the next lecture, one last time. And the last one, don't try to use dry rock velocity measurements or empirical relations derived from dry rock velocity measurements to estimate your matrix modularity of betas. And then velocities for dry and wet rocks, such as oil or gas reservoirs with brine saturated. Use the brine saturated numbers for the matrix modularity you derive from brine saturated measurements. You will get much better predictions that way.
And again, I mean, I'm just going to go just one last thing here again. The sort of danger Will Robinson, whenever you hear someone say dry rock measurements, X, okay? And again, we can talk a bit about that, and people think that has to do with desiccation and what happens at sort of the grain-to-grain contacts, that you change the nature of the cementation or the way that the grains are glued together. But it fundamentally changes the rock. So X on dry rock measurements. So.
Okay.
Well, David, how do you ensure that the rock is 100% wet when you do your
Laboratory, you mean?
Yeah.
You saturate it, and then you then you pressure the pore fluid. So you dissolve any residual gas that may be in the pore, and you flow water, and you flow that pressurized fluid through it, so as to make sure that you've got the gas bubbles. Any gas bubbles that are in there out.